In this short segment, we will talk about Contriver, an important but now outdated method in retrieval-augmented generation. While it is no longer widely used, its key contribution was introducing contrastive learning to dense retrieval, making AI retrieval faster, more accurate and scalable. Let's break it down how it worked and why it still matters. To see why Contriver was such a breakthrough, let's first look at how retrieval-augmented generation traditionally used to work at that time. And here's the standard naive RAG process. A user asks a question, which is a query, and the system uses the query to search for relevant documents using the similarity-based method, think k nearest neighbors. And then once it finds those k nearest neighbor documents, it then feeds those documents into large language model for further processing to get a response. This works fairly well as long as the retrieved documents are accurate. But there is a problem. If the system retrieves incorrect or incomplete documents, then the LLM has no way of knowing. It will just assume that the provided context is accurate and generates a response accordingly. Let's take an example. Let's say someone asks, where did Barack Obama grow up? Now imagine the retrieval system only finds one document that says Obama was a senator from Illinois. If the LLM has no prior knowledge of Obama, then it might incorrectly conclude that he grew up in Illinois when in reality he was raised in Hawaii. Even if multiple documents are retrieved, one mentioning Illinois, another mentioning Michelle, and a third about Hawaii, the system might still struggle to rank the right context and find the right document. There are ways to re-rank them, but that's a topic of RAG Fusion. We'll address that in that specific segment. So this brings us to another major challenge, retrieval efficiency. So to improve retrieval, many systems use something known as dense retrievers, which essentially converts queries and documents into their latent vector representations, and then compute the similarity scores between the queries, the latent representations of the queries and the latent representation of the documents to find the best match. So the way it's done is you take a query and convert to a latent representation using some kind of transformer. Think of it like a word embedding. You take a word or a token and find its word embedding, essentially taking a word and converting into a numerical representation, the way we do tokenization and embeddings before feeding it into a vector database, if you're familiar with that. So that's the same idea. Take a word and convert it to a vector representation or floating point representation. So that's instead of doing the embedding model, do a vector representation or the latent representation using a transformer model. Okay, this is more akin to doing those units. In units, the similar process is used to find the latent representation and then generate from the latent representation. So this is very efficient, and there is a reason why it is efficient. In traditional RAG, every word in the query has to be compared to every word in every document. So if the document has n words and the query has like k words, so it would be n times k, so it order n square effectively. It's a quadratic in complexity, and it definitely slow down dramatically as the data set grows. So to put in real world terms, imagine grading an exam where every student's answer has to be compared word for word with every page of a textbook. If the textbook is 100 pages long, you have 1,000 students, you're suddenly comparing 500,000 pages word by word. It is slow, inefficient, and doesn't scale very well. This is where Contriver makes a breakthrough. Contriver fixes this inefficiency in retrieval by introducing contrastive learning. So that was dense retrieval was when we did the latent representation or the dense representation. Now we're going towards contrastive learning. So the contrastive learning really improves the accuracy, and here's how. While the dense retrieval does work really well, in fact it reduces the order n operation to the order 1 operation, still there is issues with the similarity score or the relevance score. So in the dense retrieval, we have the vector representation of the query multiplying the vector representation of the document. Yes, we get the similarity scores, but some of the documents are not really relevant. For example, if document A mentions Obama 100 times but never states where he grew up, but document B mentions Obama only once but clearly states Barack Obama grew up in Hawaii, then the naive retrieval system will rank document A higher because it mentioned Obama 100 times. So that's the problem. Even TF-IDF will not work. So the contrastive learning fixes this problem at the source by actually training a model. they're training the model before this is before the vector database method became more popular, and all those large language models become more smarter in handling those documents. This is before that. This is probably still during the sequence to sequence models. BERT models are still popular. So they train those tiny models even before it goes to the large language models to do the dense retrieval. But instead of doing the dense retrieval, they, in addition to doing the dense retrieval, they also said that, okay, we're going to train these dense retrieval models with a contrastive learning loss. So essentially what this contrastive learning is doing is that there used to be at least three steps. There used to be query, and then there used to be a query refiner, which used to be a small fine-tune or non-fine-tune model, which, like this dense retriever, which takes the query and finds the similar documents and builds the list and then sends everything, query plus the documents, to the large language model. Now those dense retriever had that problem that we mentioned, that it gets a lot of irrelevant documents as well. And this contrastive learning essentially training those tiny LLMs that or tiny sequence to sequence models which were performing the document filtering to throw away irrelevant documents. And in order to do that, they came up with something known as a contrastive loss, which kind of looks like a precision, like how many positive documents and how many negative documents, what fraction of the total documents is positive or relevant, and then throw away everything else. So that pushes the model towards selecting the right documents all the time. So yes, it worked, but yeah, so that's the whole point. So the point of this whole Contriver method is that the query, the sequence to sequence model that used to be used before the large language model to find those similar documents to feed into the LLM downstream, that itself needed a little bit of fine tuning. So this goes back to the Replug framework, and Contriver framework is actually a precursor to the Replug framework, and we'll see Replug framework actually enhances this even further by fully fine tuning the query generation model. To sum up, the Contriver really solves this high time complexity of the previous retriever methods by converting all documents into fixed length vectors ahead of time, which essentially reduces the time complexity of retrieval from quadratic time complexity to order n time complexity or linear time complexity, which really makes it practical for massive data sets. So now that's why Contriver was a key breakthrough in retrieval-augmented generation, and then that set the stage for newer methods like Replug and RAG Fusion.